electronics design with KiCAD in the context of Fab Academy, of course. So there on the left, you can see it's a hidden KiCAD logo. It's sort of trying to get outside of there, but not really. So it's still a little bit shy and afraid. But generally, what we're going to talk about today is the setup of KiCAD, so where to download it, and then how to set up the Fab library setup. So where to put it, how to connect it to KiCAD itself, and then some basics, where to look up information about the parts that we are going to use, more specifically the ftdi 412 chip, and then of course the building parts of how to design the Hello board, which is one of the Hello boards that is available on the Fab Academy assignment page. So in order to get KiCAD, you need to go to the KiCAD website. So I'm not going to open it now. I'm just going to cover this briefly and then open it. And then the KiCAD Fab library you can find on the Fab Cloud GitLab. So there's a pub folder, and then so kind of which translates to public, and then there's libraries, and at the moment there's only electronics libraries and then the KiCAD library. And then the assignment page, so that's the one that Neil was covering yesterday. And another important part for today is the ftdi 412 pinout, which so you can use the data sheet, but for the beginning of it, since we are going to use the SpenceCon, Mega Tiny Core library for Arduino IDE, so for the Arduino development environment, so there are a few mappings that you should know about and that you can find here in this repository that you can use to your advantage in order to design the board. First things first, so where to find KiCAD? So this is the page. So when you go to kaicad.org, right? So yeah, they simplified the domain name. It used to be kaicad.org. EDA stands for Electronics Design Automation. So it's sort of a CAD. It could be also CAD for electronics, but yeah, so computer-aided design or electronic design automation, same thing. And then when you go to download, so you can download the latest stable version for whatever operating system you have on your computer. I have Ubuntu, and I think that most of you have Macs. I have been using both, and on some computers here, I'm going to install also the Windows version, so you will see that they are not that much different. Then we're going to use KiCAD together with the Fab library, which I've been iterating on for the past year. I thought it is a good idea to improve this so that the teaching could have a better flow. Because one thing also that I discovered with the original KiCAD libraries, it's probably going to be fixed in the future releases, is that when you have KiCAD, the same version of KiCAD on different systems, then the repositories or the parts that you use on these different systems, they are different, which leads, in a learning context, it leads to problems that, for example, if you make a design and then something doesn't work, and we are not necessarily in the same room, and you might send me the KiCAD project over email, or you might use the Git repository in order to upload it, and then I would download it on my computer and open it up in my KiCAD, and I would need to replace all the parts that you have there because they essentially wouldn't match. So my KiCAD, even though it would be the same version but on a different system, it wouldn't be able to load the same parts, because the parts would have different names and footprints and all of that. So this is why I thought it's a good idea to push forward and kind of finalize this, so that all of us could install the same library. And if problems happen, then there's less steps to do in order to help each other. So as you see, this library covers all the parts, and maybe even more than you will actually use during the course. So it, of course, has resistors, potentiometers, capacitors, diodes, and LEDs. All kinds of sensors like photodetectors. Then there are symbols and footprints for speakers and microphones, magnetic sensors, accelerometers. We have some memory chips there, and of course microcontrollers. I think that's the most important part for this course to understand how to use and how to design around microcontrollers. And yeah, so this is the electronics design Fab Academy page. How I see this page is that so after once you cover all the course, then you get a basic understanding of how things work, and then you might feel ready to dive deeper, so to kind of widen your horizons and understand more. And I use these pages quite often, so that just to look for some alternatives or some new things. And it's a good thing that these, so one could call them slides, it's a good thing that they are so seemingly complicated or rich with information, because it's always it's kind of an index of the good things of the internet, index of the good things around digital fabrication or Fab Academy. And as for the assignment, it's the group project or group assignment. So usually we try to do this as the first thing, but in this case, we will do it last, because before we can actually use the test equipment with a microcontroller circuit board, you should build them first. I mean, of course, I have some here next to me from previous years and all of that, but I think it is important for you to understand like at least the basics of how these work in order to be able to test them. And the individual project is to redraw an Echo Hello World board. So when you click on this link, I'm not going to click now, you will see that there are several versions. And yeah, there are the demo boards, but we need to add at least one button and a light emitting diode in order to pass. So we can click here, and as you see, there are a lot of chips, and we can specifically focus on the IT-Tiny 412 chip because it's small, it doesn't have a lot of pins, and we don't need a lot of pins, and thus it's easier to handle. And we're gonna make this Echo board, which looks like this. Or we're gonna use this as a starting point. We still need to add a button and an LED and maybe some additional features. And then as for the chip itself, so this IT-Tiny 412, as I told, I'm not gonna open up the microchip datasheet. I'm gonna go to this website, so github.com/spenceconde. But yeah, but the essential part is that you should scroll down and check the supported parts. So these are all the chips that are supported by the library. And since we're gonna be using IT-Tiny 412, you need to click here. And what we are interested in is this drawing over here. So here on the top, you see that there's VCC and ground. So this is the part where you provide voltage to the chip. So you provide power. And then there are all these descriptions of the pins. So you see from PA0 and PA1, PA2, PA3, and then there are two missing, and then it goes from PA6 and PA7. And all of the green ones, they are programmable, but some of them have special functions. The most important ones are the number 6 or PA0, which is the updi programming pin. And then the other ones that are going to be important in our case are the PA6 and PA7, which are also programmable. But these are TX and RX, which stands for communication. So when we are going to connect the ftdi connector to these pins, then we'll need to understand which one is for transferring data and which one is for receiving data. So these pins are meant for basic serial communication. This is like one of the basic ways how chips intercommunicate with each other and with a computer. And then on a computer, when we're going to connect an FTDI cable to it, the operating system is going to establish a serial connection. And through this serial connection, we'll be able to talk with the chip by sending and receiving bits and bytes. So as for me, I have KiCAD installed. And when you open it up, you have this, you can see this project panel. And I already have the project open. So today I tried out. So I did a test with the parts that we have here. So with the library, in order to understand whether we have all the things that we need. And today we're going to basically cover how to design this and how to get it to a point when it looks like this. Or this. And then also how to post-process it so that we get actually milled board. So here, this is what I tried to mill today. And by the way, I also got new milling bits. I'm still testing those, but they seem to be much stronger and better, and you can go with them basically 10 to 20 times the speed than we were going with the old bits, which were breaking all the time. So in order to use the library that I was talking about, of course, we need to go to the library website and download it. The way you do it, you can either clone with Git or you can just download it as a zip file. Here, let's just do that. Then when you go to the downloads folder, here, once we have it here, it's a good idea to rename it. Rename it to Fab. Then once you have it renamed, so this is what it contains. So it contains the fab.lib file, so which is basically the place where all the electronic symbols live. So that's for the schematic part. Then it comes together with a DCM file, which is the description file for the components. So that's in case you want to update those. So there's, by the way, a video about updating the library on the YouTube channel. Then we have the Fab Pretty folder, where you have individual footprints for the parts. And KiCAD is one of these animals which is very flexible, because normally the default schematic symbols that you have, they do not have assigned footprints. In Eagle, by default, when you put a schematic symbol, then that schematic symbol is assigned to a footprint, and it's sort of a tricky to use different like other footprints for the same symbol. But in the case of KiCAD, that's expected by default, that when you create when you put a symbol somewhere, then you should also think about, you should be able to assign different footprints to it. But in the Fab library case, in order to simplify things, they are already mapped. Then Another thing that I'm still that I just started working on are the 3D shapes. Basically, for each footprint, you can have a 3D shape, a 3D representation of the part that is gonna sit on that footprint. So for now, I have capacitors, headers, resistors, and some of the chips. So like more like packages of the chips. And yeah, and a test script over here, test py. So if you are adding to the library, then you can run this test script using Python 3. And it's just gonna test whether each of the parts in the Fab library are mapping to descriptions in the DCM file, and whether each of the parts actually have a footprint assignment and things like those. So how to use that? In order to use that, you should go to preferences, and we'll actually edit these three parts. So the main part that you need to do is to manage symbol libraries and add the symbol library file there. So you can actually, if you're going to use the Fab library, you can just disable all these in order to increase loading time, to improve loading time. But yeah, there are a lot, as you see. These are all these. And you should add one new row for the Fab library, and then you should specify the location of the library. I'm going to leave it as it is now for me. So yeah, this, then the footprint libraries. So for that, you need to specify the Fab pretty folder. So when you look it up, then you go to desktop demos. So wherever you saved the library, you should select the Fab pretty folder of the library. Once that's done, then you should click OK, of course, and then the last thing is to configure paths, because so if you want to see the 3D shapes, then you need to define a variable that is called fab, capital letters, and point it to the folder where you have the location on the disk where you have the Fab library. Once that is done, you can start out by creating a new project. And I'm going to call it Hello T412. And KiCAD creates two files for you. One is the schematics file, and the other is the PCB file. Let's start with a schematics file. Just briefly about the layout. So on the left side, you see that you can activate and deactivate the grid. So yeah, when you press and hold the middle mouse button, then you can pan around. When you scroll it, then you can zoom in and out. Right click is gonna give you a contextual menu, and left click is gonna select parts and do all kinds of interesting things. Now here on the left side, you can enable or disable grid, and you can switch in between inches or millimeters. Of course, millimeters is what we want to use. You can also enable a bit more visible cursor. But yeah, so on the right side, you have tool selectors. So all the tools that you can use in the schematics editor. In order to start out, we should take a look at the Hello Echo board and check what kind of components we have there. So we have one integrated circuit, which is labeled with this IC1, which is the AT-Tiny412. So let's start with that. I'm going to click here. You can also hit the A button to add a symbol. And yeah, one thing that was not really good with the old Fab library, and why I started to work with it, was that the parts didn't have descriptions. And when the parts do not have descriptions, they are not easy to find in this dialog box. And once they have descriptions, you can start typing, and KiCAD is gonna find them for you. And generally with the Fab library parts, you should start out by typing Fab, and then the type of part that you wanna look up. We want to look for ftdi, and here it is. Microcontroller ftdi412, and here's the schematic symbol. So there's a difference between the actual pinout, the way the pinout looks, and the schematic symbol, because schematic symbol is supposed to be more like an abstraction. It's a bit separate, like different language from the one that we see kind of on the board. So it's a language that is developed around these sort of electrical connections, and sometimes it is easier to explain connections in between chips and parts in this way. And there's a whole convention, KiCAD convention, in that kind of explains the best practices how to design these sort of symbols. And usually the rule of thumb is that you put positive voltages on the top, then negative voltages or grounds on the bottom, and then all the connections, let's say, on the sides. So if these are bidirectional or multidirectional connections, then you can put them on one side or both sides, but then usually you would put inputs on the left side and outputs on the right side. But this is completely normal. And then when you select it, KiCAD is going to allow you to place it somewhere. And when you right-click it, you can go to Properties and explore the part. So for each part, there's additional information. So there's footprint, definition, and you can also find the data sheet. That's the same thing that I showed you yesterday. But what you might be interested in is the pinout. Okay, so that's the first part. Then we go back to this thing, and we see that there's a capacitor, there's a ftdi connector, and there's the updi programming port. So let's add those in a bit faster manner. So I'm going to hit A and start typing fab updi. We see there's a updi connector already there. I'm going to put it on the left. I'm going to add fab ftdi like so. Then I'm going to add fab capacitor. So you see there's the two types of capacitors, unpolarized capacitor and polarized capacitor. The ones that you usually use to filter current for microcontrollers and different kind of other integrated circuits. So the bypass capacitors. So those are usually unpolarized. And then sometimes when you're working with monocontrollers or amplifiers, then or audio filters, then you might use more depolarized capacitors, which is a different kind of capacitor. You need to watch in which direction you put it. So you need to match the pluses to pluses and minuses to minuses. We're going to use this. So this is more like a resistor. And some of you, all of you remember this one from soldering your programmer boards, basically. So I'm going to take this capacitor. And then as for the assignment, we need to add some additional things. So we need to add a button. And we need to add an LED and a resistor. Let's add that. It's a fab button. So you see we have two buttons. So this and that. I suggest you to use this one for this assignment. So this is exactly the same that was covered also yesterday in the lecture. So, and LED, so fab LED. This and this. Like this. Okay, how to connect them together now? So as for the capacitor, I'm going to first go to this select item tool. As for the capacitor, we want to connect them to VCC and ground directly. So kind of, so in schematic, it doesn't really matter where it is located, but on the real board, it's going to be important to put it as close as possible to these terminals to filter the current through it for the VCC and grounds. To protect the chip, we need to use this bypass capacitor. It's going to make sure that the current flows smoothly into it, and it's going to give you more predictable results. In order to do that, so to move these around, you can hover those and press M in order to start to move them. So I'm just going to place it here. In order to start to draw wires, you need to hit W. So you point where you want to start the line to start, the wire to start, and then you start drawing it. And then whenever you click, it's gonna make an angle like this. And once you hit one of these little circles, then it's gonna make a connection with the part. So here we're gonna connect it to ground like this. And yeah, where does the voltage come from? So we need to kind of specify also where does the voltage come from. And in this case, it's going to be the inputs are going to be the FTDI connection. So here's going to be the ground connection. I double click here in order to finish drawing the line. And here. And I'm not going to connect those like with wires, because you might end up with a really ugly a spider net of all kinds of cables. It is much better also if you think about your schematic in a long term, that you separate these kind of into little modules, and you use labels in order to make sort of invisible mappings to specific parts of the schematic. So what we're going to do here, we're going to place a label. So one way how to do it is to click on this label icon over here, but just hover the point where you want to add it and hit L. And you can select the orientation. I'm going to select the left orientation so that the label actually is, it's kind of aligned to the right. So I mean, you need to use this tool a few times and understand how to exactly it works, but G and D. And then here, I'm going to hit label and add VCC. Like so. And then in order to connect those here, I can basically add just labels. So I'm going to add VCC here. And G and D here. Like so. Then as for so since we started with the FTDI connector, then let's continue with it also as the input point. From the FTDI connector, the two pins that we are going to use, except the ground and VCC, is going to be the TX and RX pins. And the CTS and RTS in our case, it's not significant. And this is why we can just put the no connect symbol on them, like so. And then let's use a wire again. So you can also click on this icon in order to start drawing wires. And in this case, I'm also going to use labels. I'm going to click on the label here and name it TX and RX over here. And now we need to understand which of these pins are the hardware RX and TX pins. So this is why it is important that we have this Mega Tiny Core 80Tiny 412 page open. So this is where we're gonna find the mappings. So TX is PA6 and RX is PA7. So CTR are also nicely separated. So let's draw a wire from here. And let's add a label. Let's go TX. I mean RX. And now these are connected. So what about a UPDI? So let's draw some wires from the UPDI pins as well over here, like this and that. And we can add the ground label right away. And of course, we can add the UPDI label as well there. And in order to make a connection, we need to draw a wire to the UPDI connection of the chip and add a label over here. It's going to be called UPDI. So now this header is going to be connected to the UPDI connection over here. And the last thing is to connect the button and the LED. So we first would like to move them around, say like this. And when you hit M and you move around the part, you can also hit R in order to rotate it around. We'll put it somehow next to this. Then I'll hit M and move the switch around, like so. And I'm going to use these wires in order to add extensions to those. Not like this. Like that. And then some labels. So for the button, I'm going to add a button label. And for the LED, I'm going to add a LED label. And then this. We'll connect these. And I'll draw like extra wire over here so we can connect somewhere as well. Oh. And I connected these two because basically what I need to do, I need to add both of these to ground. So I could just create a junction over here. I could just add a ground label. Like so. And then for those two, I need to connect them to the microcontroller. And we can also use this mapping in order to understand where these are going to be located. So we have PA1, PA2, and PA3. PA1 is here in this corner, and PA2 and PA3 are here. So I'm just wondering, I could connect the button to this side over here, so where the PA3 is. So I'm going to connect the button to PA. No, I'm going to choose the PA2 actually for the button. Let's do it.
Could I ask a question?
Sure.
So once you add up the label, then they connect it.
Yeah.
What?
You see this little bug up here? So that's supposed to check for connection errors. So it's like electrical rules check. So electrical rules mean that everything should be connected. So for an open connection, let's say a single label placed somewhere, there has to be a corresponding connection. And if we run this,
because
yeah, we need.
I did something wrong. For example, at the end of the wires, there's a little block, I guess, which means it doesn't connect to the label.
Yeah, could be. Or when you run this, it's going to show you what is not connected. So let's say, yeah, there are a lot of not connected pins yet, so we need to connect some. So you see that the green arrows, they point to, they usually point out different things. So in this case, it is that they are not connected. And then probably here where there's button, so this one. So it also tells you that, hey, there's no corresponding connection for this net. So it's button and LED net. We are about to fix that. So how was it? PA2? Yeah. So let's connect the button to PA2. And then the LED here. And so here's the challenge. I mean, we could add another LED actually to the PA3, but I'm just gonna leave it so like this, or you just add some sort of a header there in order to make it a reusable, reprogrammable pin. So it's up to you how you want to do it. And now, so as you saw, I was running this annotate schematic symbols button. So it's important because when you just place the symbols here, instead of these numbers, they're going to be question marks. And according to how you place them in the schematic, KiCAD is going to decide what numbers to assign them. So because like these designators, so J, which stands for jumper, and U, which stands for integrated circuit, and SW, which stands for switch. So these are the same, let's say, for all the switches, but then the numbers, they are different. So if you have multiple switches in your circuit or multiple LEDs, like D stands for diode, and LED is like a light emitting diode, then yeah, these numbers are gonna go from 1 to infinity, depending on how many of them you have in your design. And then yeah, once you press this, so these numbers are being so the KiCAD is figuring out these numbers, and then you can press this debug button in order to check the electrical rules. And now we see that there are 2 errors, and basically it complains about some weird thing. And it took me a long time to understand this one and to look up documentation about that. So in KiCAD, it is important to specify where the power comes in. So even though we know that the power comes from this FTDI connection, so we need to explicitly specify where the power comes in by using power flags. And this is why this power port tool does. So you select that and then you click somewhere, and it's going to open up this dialog box, and we need to look for power flag, this one. And what we need to do, I'm going to hit M to select it so I can move it around. I'm going to hit R to rotate it, and I'll connect it here. So, but actually, like I should just put it here, just where the power input is. So ground is one power input, and instead of opening the dialog again, I can just hit C for copy it, and move it to the other power input that we have here, which is the VCC, the voltage, the positive voltage input. And now when I hit debug and hit run, there are no errors. Our schematic is ready. I can hit save. And usually if you're using the default KiCAD symbols, you will need to assign footprints to the symbols that you have laid out here. And then this, yeah, this is what, this is the footprint assignment dialog or tool. And normally you would have these empty. So you see there's C. So there's the designator, so C1, capacitor 1, D1, jumper 1, jumper 2, and so on. And usually these fields to the right, they would be empty. But in our case, they are already mapped. So since we are using the Fab library, so for each of the symbols, for each of the Fab symbols, there are already footprints assigned, and you can actually take a look what are these footprints. So you can right click and then click on View Footprint, and it's going to open up you the footprint editor and going to show what is the footprint like. So this is sort of a unrealistic representation, so you cannot really understand how big it is, but you can use this measurement tool over here. So just a digital caliper, let's say so, and it's going to allow you to actually measure distance between 2 points. And you can, let's say, take this point and then go over here. You will see that this distance is, let's say, 4 millimeters. And the resistor itself, the capacitor itself, is going to be around 3.2 millimeters, like this. And I think like underneath you could actually see somewhere. You can close this, and most interesting part is probably this one.
Sorry.
Not most interesting, one of the most interesting. So here with this header, so when I was drawing it, I skipped. I didn't draw the actual pins that are facing outwards, because that makes it problematic to produce the board for PCB milling. So I'm gonna get to this later. But here, what you can also do, I think you can check the 3D footprint somewhere. And then for the button, the footprint is gonna be like this. And then for the ftdi, it's gonna be a generic package, which is called SOIC 8. Like so. And it's always good to double check whether all of these are assigned. And I think when you export the net list, which is the next step, then KiCAD is going to notify that something is not right in case the mappings are not there. So the next step is to click on this net list icon and generate net list, and should put it in the same folder, where the same project folder, which is also opened by default when you hit it. You hit save. And then once you have your netlist, you can move on to the PCB new software part of the program by hitting this button. It's going to open up you the PCB editor. And as you see, it has like this red frame, sort of a page layout with old style. You're not going to use any of this. I wonder if you can hide it. It doesn't matter. But in order to open the netlist and the parts, the footprints that we're going to be using, you have to click on the net icon. And then here you can select the netlist, and then you hit open and update PCB. And then you can close this dialog. And then you should place this somewhere in the middle of the page. When you zoom in, you will see all these parts, which are by default selected. You should unselect them by clicking somewhere. And you can start laying them out. So you see these pins, so the different pads are connected by white wires, and these are sort of guides for you to see which parts should be connected in which way. And when you select so one of these pads and then you hit M, then you can start moving these around, and rotation is done by hitting R. And let's move the parts somehow. We can actually see them making sense. usually put the microcontroller somewhere in the center. Then the next thing is that we need to put the capacitor as close as possible. So this is important with the chips, that it should be as close as possible to the chip itself. And once you zoom in, you'll notice that the parts are snapping to a grid. And at the moment we have the grid, it allows you to move parts in 1 millimeter steps. So we can reduce that to, let's say, 1/4 of a millimeter to 1.25 millimeters, maybe even 1.2. Now select and hit M, move it a bit closer. And the updi connection, I'm gonna put it somewhere, say, yeah, the button. I'm gonna put it somewhere here, maybe. We'll make a longer board, so I'm gonna connect the button somewhere here, so we have like a long, thin board. And this one. Then the LED, you see, should connect it somewhere here. I'm gonna rotate it around so that's can be connected here. You can also shift select some elements and then hit move, or you can also drag a rectangle around them and then hit move. Then here, so it's going to be easy to identify the edge of the board because of these connectors, of the way the connectors are drawn. It's kind of help you to see where the edge of the board is going to be. Okay, so this looks good enough, I guess. And the next is to use the root tracks tool in order to route the copper wires in between them. But before we do that, it is important to make sure that we have the track widths set right. And for PCB milling, we want the tracks to be a bit thicker than 0.25 millimeters. And for that, we're going to go to this edit predefined sizes option. So in order to access this, you have to click here and then predefine sizes. And we need to click on the net classes item over here. And then where we have clearance, we should specify 0.4, as this is the average tool size that we're going to use for milling the PCBs. And then the track width, we're going to set to 0.4 as well. We don't need to touch the rest of those. So we're gonna, if we would be making a double-sided board, then we would need the vias, but this is just fine. So we hit OK. And we can start drawing these. And the way you would approach this, the rule of thumb here is that you should try to connect the the communication lines first, or let's say that you would like to connect the LED or button. So I usually also route the voltage, the positive voltages, but I leave the grounds open for the last step. So where I'm gonna use a special way of connecting those, which is also gonna help to denoise the board, protect the connections from the interference. And then, yeah, these TX and RX are important. So RX, connect. Oh, not really like this. Then TX, and as you see, I'm going under the chip, so that's all legal. Can route under the chip. And the positive voltage has to be connected somehow. If you don't like the layout, so there are ways to move those. So it's not really as straightforward as Illustrator, because you see when you move around a segment of the track, then sort of loses connection with the other ones. So if you want to keep it in place, then you should use the drag tool, and you can access that by selecting the track that you want to edit, and then hitting D. It's gonna drag the respective points and lines to match your design. And I'm also going to connect this VCC to here, but in this case, this is wrong, because I want the voltage, the positive voltage, to go inside of the chip, into the chip through this capacitor. So what I'm gonna do is I'm gonna somehow route around. I wanna connect it first to this VCC chip. So well, I'm still gonna make space over here. And it seems that almost everything is connected. So I'm gonna connect these two button pins. Everything is connected except the grounds. And yeah, before I deal with them, I'm gonna draw an outline of the board. So in order to draw an outline of the board, you should use the graphic lines tool. And I suggest you to change the grid to something that is like whole millimeters or half millimeter. It's going to allow you to orient yourself, figure out the size of the board in terms of millimeters easier. So I'm going to just put a millimeter offset from here, start drawing downwards. And then I'm going to put one line here and around the ftdi like this. Like so. And in order to make sure how big this is, I'm going to use this measurement tool. I'm going to delete these dimensions after, but just to give you an impression how you could check the size of the board is. So you see it's like 19 by 34.5 millimeters. I could actually save some space by moving this ftdi connector a bit inwards. So maybe let's do that. Okay. So then I can edit the outline also just by moving it. This is way much different than Illustrator or any of the drawing programs that you have been using. So you have to spend some time with it in order to get used to it. And then connect the ends of the lines to the corners. All right, like this. And so how would I deal with the grounds? So what I usually like to use is this add filled zones tool. And when I click on it, then I have to choose a point where I would start start drawing a polygon. And it's gonna allow me to, well, should be also on the correct layer. So you should select layer. Yeah, so about layers. So here on the right side, you can see different layers that you can find on a PCB. So if you look at the PCB as a sandwich, then on a double-sided PCB, you would usually, so if you would go to a manufacturing house in order to produce those, you'll find most of these layers. So the FCU stands for front copper, BCU stands for back copper, then there are adhesive layers, then there are paste layers. So these are for the solder paste. If you are so if you are using the reflow technique, so you apply solder paste on the whole board at the same time, and then you pick and place components, and then you put them in the oven. And silk screen, that's for these the blue color, the blue colored items and lines. This is silk screen. That's what's usually going to be printed on your board in terms of visual information. Then mask, that's for the solder mask. So this is for to produce the solder stencil. So in order to apply solder paste to your board in a real manufacturing setting. And then there's a drawings user, which we're going to use later in order to produce some custom drawings on the board. More like that's kind of a hack in order to make these boards fabbable, so to say. Then there are edge cuts, these eco layers. I'm not sure what are these, but we're going to use only the front copper and drawings user layers, and also the margin layer in your designs. But yeah, in order to create these copper fills, we need to select the front copper layer. And also, we need to select this layer again in order to make sure that the copper fill is going to end up there. And we want the fill to represent the ground net. So we want to connect all the unconnected grounds together with this copper fill. And we can specify some clearance. We'll specify as 0.8. Minimum width, we'll specify as 0.4. And the thermal clearance as 0.5, because it has to be bigger than the minimum width. Okay, and then I'm just gonna start to draw the polygon by snapping to the corners of the board outline. And this is what we end up with. You see all the grounds are connected, so except we need to finish up these connections over here, like so. And at this point, we can hit this little bug icon again, so which is a design rules check. When we run it, we can see whether there are any errors. And this is not good for learning because there are no errors. So let's leave something disconnected like this, for example, and run the debug thing. And it's going to show us one unconnected item. So unconnected items here. It's going to center that in the page. This is our unconnected item. Close and connect it again, like so. Just to double check. DRC. So 0. So design rule check is going to check whether there's enough distance in between the traces, whether the copper is nicely following around the pads. So one thing that we notice here again is that we don't want this ground pin to be connected to ground directly. So we want somehow to guide the electricity through the capacitor and so that it passes into the chip. So in KiCAD, there's this other icon, so which is the keep out areas. So and we can specify some areas where the copper shouldn't appear at all. And in this case, we can use this in order to make sure that the copper fill, and we'll specify 0.2 as the grid in this case, the copper fill, so copper 4. Now select this keep out copper 4 item over here. I'm going to make sure that the copper 4 doesn't disturb us around the chip. And once this is done, you can hit B to process the copper 4 again. And here I can just make another connection. And Now there's a problem. The copper keep out area is not letting me to draw a via to draw a connection. And I don't want to keep out tracks. So like this. Now we can draw a track over here like this. And as you see, everywhere where there's ground, this ground pad is connected to one big ground area. Yeah, we can, of course, like make sure that these kind of things do not happen, but this is not that bad. So it's not connected and it's not going to cause any trouble. So this is fine. What is going to cause trouble are these elements that are outside our fabrication area. So what you should do, you should somehow move them inside. So these are not going to affect the final design of yours, because eventually we're going to just hide the layer where they are located. So in this case, it's the fab layer. And also, we do not care about the silk layer, really. And we do not care about the courtyard layer. And the way we are going to produce these traces file, so when you go back to the assignment page, and you will see that there's this traces file. So we need to produce this in order to be able to produce toolpaths with mods. And in order to do that, we will need to use this file export SVG option. But at this point, it's going to generate as a file which doesn't have any margins. So just for example, I'm going to export one SVG and export front copper and edge cuts. I can open it up. What I'm trying to tell is that mods is gonna have a hard time trying to figure out paths around it. So you will be able to mill the traces with mods, but you're not gonna be able to move the tool outside the area because there's no margin. And we need to figure out a way how to add that in KiCAD. But that, it's a bit of a hack. I use the margin layer. To get a margin, I switch to the polygon tool, making sure that we are on the margin layer. And I switch over to the grid of 1 millimeter. And I'll be adding 2 millimeter margin around. So I'm going to count. So each of these points is 1 millimeter. So 1, 2, and we have our margin. Another thing, if we look at the files, is that in mods, this one, that in mods, instead of empty rectangle, we need a filled rectangle. And in order to have that, we are going to switch over to the drawings user layer, and we select this filled polygon tool. I'm gonna draw over this one so that we have a filled polygon. One essential, maybe not essential, but important thing if you are after correct size of your board is that you select it and hit E for edit and edit this line thickness and edit it down to 0. You can select back the front copper layer. And just for you to see the difference, I'm going to rename it. I'm going to add these. So that we do not overwrite them. Maybe like this. And I'm going to go to file, export SVG. And yeah, it is important to understand where things go. So you need to specify an output directory, and this output directory is going to be relative to your project. And then you need to select which layers you want to export. And by default, the front copper is selected. And instead of the edge cuts, we want the drawings user layer to be exported. Default pen size is fine. We want to have it black and white. We want to have the board area only. And we want to have one file per layer. You can hit export. You see there are two new files that appeared. And if we open them up, you'll see. So this is the new file. This is the old file. No, not this one. This one. So you see it doesn't have a margin around. And then this one has. And so the margin also, and the fact that we have all the elements placed inside the board, it also makes sure that everything, so that all of the layers are going to be symmetrical. So this is going to be especially important if you choose to make a double-sided board. And here also there's a margin around, like so. Then here there's only a line. There's an empty file basically. So you can close this. Yeah, close that. And the next step is to use mods in order to produce toolpaths. So we go here and we go to mods.cba.mit.edu and we right click and select program, open server program. We should go down to srm20 and select the pcbsvg option in the browser. And then we select the SVG file, the SVG folder. We need to start with the front copper one, open. And if you look at this, no, this one, you'll see that the traces or the connections in between pads and LEDs are white. And this is how it should be. So the white areas is the copper that we want to leave on the board, and the black one is the copper that should be removed. So, and in this case, it's inverted, and that's why there's the invert button in order to give it an opportunity for you to do it on the fly, so without using any external program. And we want to again use the mill traces option, and I'm gonna stick to using 0.4 millimeters for the traces, for milling the traces. This also goes for the new tools. And 0.1 for the depth. And for the offset, I'm gonna leave it 4. And here again, the same. So for the new tools, you can go up to 20 millimeters per second. Mills really well. But for the older ones, stick to the values that I showed you before. But I think like once you come to the lab, so just feel free to bug me and ask how to do it with the new tools, because it's so much better and faster. And we can hit delete here. We can add a new module. We should do that. Server module that is under the file category. Save. We connect these together. And at this point, we're ready to hit calculate. Here's our toolpath. You can double check it. Yeah, things seem fine. Yeah. And also, Why didn't it ask me to save it?
Actually,
did it?
Chris, there is one more line extra on the file. Ranjit just showed me last time. Like if you go to modes and like on the output,
Yeah.
there is one extra line that's coming out from the output side. Usually it doesn't work if there is a double line.
Which? Ah, there.
Yeah, that
Okay.
the other one, you can delete that one.
Wait, how do you disconnect it?
Like if you double click on it, I think.
Ah, here we go. Thanks. Some modules, server module, file save, this and that. Somehow doesn't want to connect. And now it connects. Mhm. So it might be because of the double line. Yep. And we can save it. And then as for the outline, we need the drawings user file. And this zoom thing is floating around over it. Yeah, and again, the same thing. So instead of a black rectangle, we want to have a white one. And this is why it's also important to add this margin in KiCAD so that the mods can actually go around the white area and generate toolpaths. And then here we're gonna, we can still go with the mill traces. And what I discovered today is that for the mill, so for the outline milling, we need to use an 0.5 0.5 diameter. And then for the cut depth, you should use 0.2 millimeters. So it's going to be the step down. And then for the full depth, you should use 1.8 millimeters. And offset number is going to be 1. And then we can actually do both things. We can do the traces and the cutting with the same tool. So we can set up the tool once, and then we can cut. We can mill and cut the board in one go without changing the tools. It's really convenient, and as I told, it's 10 times faster, and the tool doesn't break. So here again, leave the same 20 millimeter per second, and we hit calculate. Same. I wonder, did it open it here? Yeah. So this is a toolpath. So it's gonna go 0.2 millimeter step downs, and just multiple times really quickly around. So as you see, much faster. Yeah. And that's pretty much it. So then you can copy and rename files. Yeah, here we go. So I'm going to select these two, cut them. Electronics design. Folder SRM. Paste them here. I'm going to rename the first one to traces. It was 1.4 millimeters and 20 millimeters per second. And then the other one was cutting in the same tool, but I set it up as 0.5. So I'm not sure what value to choose here, but basically you can use the same tool and the same Z and XY origin, and also 20 millimeters per second. And then you load these into the srmd panel, and off you go. And then also, whenever you have a question about the library, let's say you're using the part and it doesn't exist there, you can add issues here directly in the KiCAD library repository. So you can go to issues, and you can create a new issue. No issues, yes, I believe that. You can create a new issue, like it doesn't work. And then you specify a little bit more in detail what doesn't work. So the store is 3D footprint is missing one side. Screenshot attached. Like this. So these GitLab issues is a really nice and organized way how to work with issues in a way. And then if I need more information, I can always respond to this. Yeah, use this issue tracker. And actually, yeah, for the, all right, so it's 5 o'clock. Thank you. Otherwise, see you around.
See you.
Bye.
You.
Bye.